And so I figure we should talk about trig, and before we can really talk about antiderivatives, we have to refresh our memory about derivatives with trig. So if somehow you made it this far and like didn't memorize all the trig derivatives, the time has come. I will say that really, honestly, most of the time we're dealing with sine, cosine, and tangent. And yeah, there are times when we're going to have to worry about all of the trig stuff, but most of the time we're dealing with sine, cosine, and tangent. So I'm stalling for time, trying to fix my video once again, as is usually the case, but you don't have to wait for me to write derivatives. You know what these derivatives are. Go for it. Dun, dun, dun. So derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is secant squared. Now, just also to refresh our memory in terms of derivatives with trig, let us not forget that we might have to employ some chain rule. So if I had something like the derivative of sine of 5x, then that's going to look like cosine of 5x times 5. Now I'm putting parentheses around the 5x. Calculus cannot change the argument or like the angle or what's inside of a trig function. Only trig identities can. So if you're doing any kind of calculus, whether that's derivatives or antiderivatives or limits to a trig function, it never changes what's like inside. Now, the reason that I'm multiplying by the 5 is because we have to do chain rule. So I'm taking the derivative of the sine part. Derivative of sine of something is cosine of something. And then we're multiplying by the derivative of the inside. Similarly, if I was like doing a derivative of cosine x cubed, I'm going to look at that cosine and say the derivative of cosine is negative sine. Calculus can't change what's inside, so that still has to be an x cubed, but the chain rule would tell me to multiply by 3x squared. And of course, this is only 3 of our lovely trig derivatives, but wait, there's more. So if we add in the derivatives of the other like co-functions or reciprocal functions, we would add to this list the derivative of cosecant of x, the derivative of secant of x, and the derivative of cotangent of x. Now, the whole reason that I'm reviewing derivatives is because we're about to start doing this backwards and finding antiderivatives. But the derivative of cosecant of x is negative cosecant of x cotangent of x. And the derivative of secant is secant of x times tangent of x. And the derivative of cotangent is negative cosecant squared x. Just as another like refreshing our memory about chain rule fun, let's say that I was taking the derivative of secant of 7x squared. When we take that derivative, I know the derivative of secant of something is secant of the thing times tangent of the thing. And the thing to be careful about here is calculus can't change what's inside. So we're still going to have that 7x squared inside of both. And then we'll have the chain rule part that says, what's the derivative of 7x squared? 14x. Okay, I'm pausing there for a second before I move on to do all of that in reverse. In case we got questions or anyone wants more practice with trig derivatives. Not seeing anything in the chat. Not seeing anything in the room. We'll go ahead and move on with our lives. Oh, can I write out the chain rule for reference? I could, but as a formula, it looks dreadful. So I really think that chain rule is better explained with examples. But if you are someone that likes formulas and it's helpful, if I had f of u of x, and I took the derivative of that, this would look like f prime of u of x times u prime of x. I think that looks terrible as a formula. But if that's helpful, that's technically what the chain rule says. What I think is more important about chain rule is that it says we're going to take the derivative of the function and then multiply by the derivative of whatever happened to be inside. So if I had something like y equals 3x squared plus 4x to the 7th, then what chain rule tells me to do is to kind of look at the overall structure that says I have something raised to the 7th power, do that derivative, which would be 7 times something to the 6th power. And then the chain rule piece is that we multiply by the derivative of whatever that sort of inside function was. And that's true whether we're talking about stuff raised to exponents or if we're talking about trig. So if this could be something really gross and I could have like, oh, let's make it really gross. No, moderately gross. Let's say that I had tangent of x cubed plus 1, and then that whole thing was to the 4th power. From a chain rule perspective, I've got garbage raised to the 4th power. So I'd end up with 4 times that garbage raised to the 3rd power. And then we kind of peel the layers off. So when I peel that layer off, the next inside piece is the tangent. So I'd be thinking about, okay, what's the derivative of tangent of something? That's going to be secant squared of the something. So now I've kind of peeled that layer off and peeled the tangent layer off. And finally, I'd be taking the derivative of that very inside piece, or 3x squared. You're not going to have to do gross derivatives at this point, but we might have to recognize chain rule because that's really what's happening when we have a U substitution, is that there was some sort of chain rule that got us there in the first place. Okay, we're going to go backwards. Yeah. At some point, the trig stuff, the derivatives and the integrals, if you really do just want to memorize or put on a page of notes or something, but let's go through the nice ones. Now, the nice trig integrals are not the same as the nice trig derivatives. So when I write the integral of sine x dx, that's saying whose derivative is equal to positive sine. And that's going to end up being negative cosine of x plus a constant. Let us not forget the plus a constant. I've got the integral of cosine of x dx. that's going to be asking us whose derivative is equal to positive cosine. And that's sine of x plus c. If I had secant squared x dx, that question is asking whose derivative is equal to secant squared. So the answer there is going to be tangent plus a constant. The integrals of tangent or secant of x or cosecant of x, they're all gross because they're not somebody's derivative. The integrals or the antiderivatives that are nice are the things that already are somebody's derivative. So when we see something like secant x, tangent x, we should be thinking whose derivative is that? And I would say those four are the most common antiderivative problems that we end up with. Okay, but I want to think about all of these more generally, especially at least thinking about them with a number. And what I mean by that is if I'm looking for the antiderivative of cosine of 5x dx, technically you could do a u substitution on this, but I don't think that it's worth our time. I think this is one that we want to get to a point where we can just kind of write down and see it. So my first step here is to think about, okay, well, whose derivative is equal to cosine? It's going to be sine. Calculus can never change the argument, so I'm still going to have a 5x inside. But if this were the right answer, then when I took the derivative, I should get this back, and we don't. Because the derivative of sine of 5x would be sine of 5x would be cosine of 5x times 5. So we fix that when we take the antiderivative by dividing by the constant. So when we were taking derivatives of the trig functions, we end up multiplying by that constant because of the chain rule. And when we're taking antiderivatives, we end up dividing by the constant to sort of undo that chain rule factor. Similarly, right, same kind of thing works if I've got secant squared of 3x dx. I look at that and say, whose derivative is equal to secant squared? Oh, it's tangent. So I'm going to have tangent of 3x and divide by 3 to take care of that chain rule. Now, if that doesn't sit well with you, or you're like, yeah, I'm never going to remember that, that's okay. We can get to the same place by doing a u substitution. It just takes a little bit more time. But if I did that as a u substitution, and I just had this secant squared 3x dx, I could say, oh, hey, does the derivative of one part equal the other part? And it kind of does, because the derivative of 3x is kind of dx. If I let u be equal to 3x, then du would be 3 dx. And although I don't have that 3, it does mean that I can rewrite that as 1/3 du is equal to dx. Now I can change the problem we've got into saying secant squared u times 1/3 du. And I went ahead and put my 1/3 out in front of the integral. You could leave it inside. Doesn't matter either way. And then I'm going to end up with, sorry, switching colors too soon, 1/3 tangent of u plus c. And then to get all of our points, making sure that we plug back in what u was equal to. And it is totally fine to get there this way. But I recommend that if it's just a number, that we not go through all of those steps. That when it's just a number, it's a lot faster to go straight to just dividing by the thing. Good times. So if it's more than just a number, like some of the problems on your homework, then I am definitely going to want to use a U substitution. So let's say I've got something that looks like, I'm going to make this a little bit gross. Sine of x to the negative fourth over x to the fifth dx. And my integral symbol down here a little bit further. Well, for starters, I'm going to walk up to the problem and say, that's gross. It's not just straight up somebody's derivative in terms of trig. So I'm hoping for a U substitution. There are two pieces in this that are kind of gross. There's the fact that we've got a fraction. So we've got that x to the fifth on the bottom. And then there's that x to the negative fourth inside of the sign. If you're not sure where to start with the U sub, just pick one of them and see what happens. So if I were to pick x to the negative fourth, because I would much rather clean up the sign part, the trig part, then when I take that derivative, I'm going to get negative 4x to the negative fifth dx. And you might look at that and say, oh, we don't have that in the problem. But wait, we do, if we're clever and rewrite this. So this is the same as saying negative 4 divided by x to the fifth dx. And I have this part. I just don't have the negative 4. So we can rewrite this as negative 1/4 du is equal to 1 over x to the fifth dx. I will let you all finish it off on your papers. While also spilling water on myself. That's an important component. I was going to have people on Zoom type an answer in the chat. This might be hard to type in. I don't know. What do you think? Should we finish it together? Okay. So I'm going to rewrite this. And unfortunately, I'm like squeezed in and running out of page here, but we're going to make this work. So that dx over x to the fifth, that part is what's going to become negative 1/4 du. I just out of habit tend to put the negative 1/4 in front of the integral. You don't have to, but for me, it just keeps it less cluttered inside. Well, since x to the negative fourth is what we swapped out to be u, that makes this sine of u du. And that's not so bad. Now I'm looking at that and saying, great, who's the function whose derivative is? And if you want, we can steal the negative from out front, because we have a function whose derivative is negative sine of u, and that's cosine of u. So I'm stealing that negative to get cosine of u plus c. And then because I actually want all of my points on the problem, I'm going to go ahead and make that say 1/4 cosine x to the -4 plus c. That is going to be my final answer. Yeah, that's a good question. Tricks for remembering the trig, the derivatives of the trig functions. Doing 40 problems in a row. I mean, like, really, that's kind of what my answer is. There are certainly some patterns, but I feel like the patterns aren't really helpful in trying to see things backwards, right? So when you're doing the derivatives, all of the co-functions are negative, which means that when you do antiderivatives, it's actually all of the not co-functions that end up being negative. I don't know. That's not particularly helpful, right? I really do think just doing a whole bunch of problems is probably the best way to get it memorized. A few years ago, a student told me that they like had a deal going with their roommate. Their roommate had to memorize a bunch of stuff for bio, and they needed to memorize like derivative stuff. And so they like they made a pact that they could quiz each other at any point in the day, and they like had to put money into a jar if they didn't know the answer. So, you know, if some money on the line would help for memorizing them, just saying it works for someone. Yeah, I mean, yeah, I got nothing. We just have to do more problems. That's all I got. So let's do more problems. Do we want to do kind of a gross one? Just a little bit gross, not super gross, but let's talk about what the integral of tangent is. So the thing is that when I look at this, I would be trying to think, well, whose derivative is equal to tangent? There is no trig function whose derivative is equal to tangent. That's why this one's gross. But what's also important, in addition to having those derivatives memorized, is having sort of other forms of these trig functions memorized. So tangent of x is the same as sine of x over cosine of x. And the magic of rewriting it that way is now I can ask my usual U substitution question. Does the derivative of one part equal the other part? And it does. Now what's tricky here, and maybe don't take notes for a second because I'm going to do it the wrong way and the right way. You probably only want the right way in your notes. So if I looked at that and I wasn't sure, right, option one would be to let u be equal to sine of x, and that would make du cosine of x dx. But when I look in the problem, the cosine is on the bottom. So if I try to like somehow make that substitution, I'd end up with like a du down here in the denominator. And that's not going to work as an integral. As a general rule, if we're doing a u subs, no, this like, no, we're not going to make a general rule. We're just going to say, no, this one will work. As a general rule, du should not end up in the denominator. That often means that it's the smarter choice to choose the denominator as u. Doesn't always work out that way. In fact, like literally the previous example I did, it didn't work out that way. But the du shouldn't end up in the denominator of a fraction. So this is really the way you want to do it. You can take notes now. So if u is equal to cosine of x, then du is negative sine x dx, which I almost have on top. I've got the sine x and the dx. I just don't have the negative, which means negative du is equal to sine x dx. Well, when I rewrite this to be in terms of u's, that makes my integral say 1 over u times negative du. And this is the special one. This is the special one that we're not going to rewrite as u raised to a power, because 1 over u du is natural log. Sorry, 1 over u du, the integral of 1 over u du is ln of u. So this becomes negative natural log absolute value of u plus a constant. And then I can put the u back in there to say negative natural log cosine x plus c. And this would be totally fine, but I will tell you that this is not the answer that you will see in like a reference guide or the book in terms of what the integral of tangent is. Because what the book decides to do is to use log properties to manipulate this. So that negative in front, we can pop inside as an exponent and turn this into natural log of cosine x to the negative 1. But that's the same as saying natural log of 1 over cosine x. And 1 over cosine x has a special name. That, my friends, is secant. And if you are looking in like a table of integrals in the book or online, you will usually see that the integral of tangent of x dx is written as natural log secant plus c. It's not wrong to write it as negative ln cosine of x. It's just that's not usually how you're going to see it in a table. More fun with trig? So let's say that I had, how about sine to the 5th x cosine x dx. This is a notation thing that I maybe have taken for granted, but this notation of putting the 5 up there before the x, you've probably seen in 16a, but that means that we have sine of x, like the entire thing to the 5th power, cosine x dx. And that's just a notation choice. Probably it got made like early days of textbook printing or something. I don't know, but someone made up that notation choice. Well, if this is the case, and I'm looking at sine to the 5th times cosine of x, I am falling back to asking myself the same dang question. Does the derivative of one part equal the other part? And the answer is yes. Anytime I've got sines and cosines together, one of them is the derivative of the other. And we kind of have a choice to make, but just remember u stands for ugly. And this part's a little bit uglier than the other because we've got something to the 5th. So I'm going to let u be equal to sine of x, and that's going to make du, derivative of sine is cosine of x dx. And I will once again give y'all a minute to try that on your paper. Make the substitution and then finish off the antiderivative. Okay, I have no one brave enough in Zoom to throw an answer in the chat. We'll just go for it. So if I make my substitution, I've got u to the 5th du. And when I integrate that, I'll end up with u to the 6th over 6 plus some constant. And we're going to swap back in our sine of x. And I would write that as sine to the 6th x over 6 plus a constant. You could also write that as 1/6 sine to the 6th x plus a constant. Either way, take your pick. We have about 20 minutes left, and I thought we could also do some practice with exponential integrals, since homework 9 had a mix of trig stuff and exponential stuff. But I can make up trig integrals all day long. So if people want more trig integrals, we can do that too. Anyone have a vote? Doesn't matter. Let's do some exponential ones. And I can make them tricky or not. But let's start with not super tricky. And let's start with like, I know that I've already done a couple of these, but I do want to try to just help drill it in that if I'm taking an integral and whatever is going on in there. Oh, and there are some questions in the chat. I'll go back to the previous problem in a second. If I have a number times x in the problem, it's totally fine to write out that u substitution. But we're just going to end up dividing by that constant. So save yourself the time and head straight to that answer, or think about this generally as saying e to the a times x dx is equal to 1 over a e to the ax plus c, where a is a constant. Because that same thing happens whether I'm talking about exponentials or I'm talking about trig functions, or even if I'm talking about something like 5x to the 7th dx. The same thing is going to happen here. That 5x, when we do that u substitution, will give me a 1/5. Or cosine of 7x dx is going to give me the 1/7 sine 7x plus the constant. Okay, going back into the chat. There is a notation question about the previous problem. That's not the previous problem. I know which direction pages turn. Okay, notation wise, and honestly, it's just like some old dead white guys decided this. I have no better answer than that. But when I put the number here, that means that I have sine of x, the entire quantity to the 6th. And when I put the number here, that means it's sine where the angle was x to the 6th. So they just mean different things. And it's just a notation thing. We didn't get a choice about it. Some old dead white guys made that choice. We're stuck with it. Yeah. Hopefully that answered the question. You are always safe using parentheses and not having to worry about either of the notations, right? You can always just throw parentheses in to make it clear which thing you're talking about. Okay, if we got the basics down. In terms of what happens with those constants, let's make these a little uglier for some exponential problems. There's kind of a, yeah, here we go. I got something good planned. How about I think I have something good planned. Well, it looks gross. I've got 5e to the x divided by the quantity e to the x plus 4, that thing squared dx. Yeah, it definitely looks gross. And anytime I am staring at something that looks gross, I'm thinking to myself, hey, does the derivative of one part equal the other part? Kind of, sort of. One of the things to remember whenever we're dealing with integrals of e to the x is that e to the x is its own derivative. So when I look at this, I can take that part on the bottom, that e to the x plus 4, and that derivative is just going to be e to the x dx, which I have. And that means that if I rewrite this, I've got that 5, which I can leave on top or pull out in front. It doesn't matter. But I'd have 5 divided by u squared du. I would choose to rewrite that to say 5 times the integral of u to the -2 du, just because it's easier for me to like follow the pattern of add 1 to the exponent, divide by the new exponent. So if I add 1 to the exponent, I'd have u to the -1, and then we'd be dividing by that -1. We don't have to, but when I rewrite this, I would probably choose to simplify it a little bit, because when I rewrite it, that u to the -1 tells me it's in the denominator, and I can take the -1 from the denominator and actually bring it up with that 5. So I'd have -5 over e to the x plus 4 plus c. What if we end up with exponentials and trig all in the same problem? Something like e to the 3x secant squared of 2e to the 3x plus 4. Wouldn't that be gross? Yeah, that actually is pretty gross. But we got this. I'm going to look at that mess and say, I sure hope the derivative of one part equals the other part. And then I'm going to take the messiest part of that and set it equal to u. Now you might be thinking that the messiest part is secant, but actually in the scheme of things, secant squared isn't bad because that is somebody's derivative already. The messy part is all that garbage inside of the secant. So I would let u be equal to 2e to the 3x plus 4. Because my derivative then would be 2e to the 3x times 3 because of the chain rule dx. And that 6, I might not have that out in front, but we can fix that. I will once again let you make the substitution and then finish off the antiderivative, which will stall for enough time for me to write a really gross one. Might have come up with something too gross. But it's a good one. Okay, I stalled for time. I don't know if I give people enough time, but if I rewrite this, that e to the 3x dx part, that becomes 1/6. And I've got my du. And then the secant squared now has a u in it. Then I'm asking myself, whose derivative is that? That's the derivative of tangent. So I'd have tangent of u plus a constant. And then swapping back in 1/6 tangent of gross 2e to the 3x plus 4 plus c. Okay. There are two kind of tricks that I want to show you in terms of exponentials because they're helpful sometimes. But I don't necessarily want to get too into the weeds of how gross the problem can look. So I wrote one, but it's pretty bad. So I'm going to change it and make it a little bit better. So honestly, I'm looking at this problem. It doesn't look too bad at the start, but if I ask myself, does the derivative of one part equal the other part? That's a no, because I don't have another e to the x term in here. So the trick is to creatively multiply by 1 and give ourselves another e to the x term. So what I'm going to do is to multiply the top and the bottom by e to the x. Well, on the top, that's going to leave me with an e to the x. And on the bottom, something clever happens when we multiply this out. So e to the negative x times e to the x, this is one of the tricks that I wanted to point out. E to the negative x times e to the positive x would be e to the negative x plus x, or e to the 0 or 1. That's a helpful trick. The other helpful trick that doesn't happen in this problem, but if I had e to the x squared, because powers raised to powers mean that we multiply, that's actually just another way of writing e to the 2x. Well, e to the 2x is way friendlier to deal with, whether it's a derivative or an integral. I'll take e to the 2x all day long over e to the x squared. So just kind of two things to look out for. Okay, so down here on the bottom, e to the negative x times e to the x. When we multiply those together, I get 1. And then 1 times e to the x, I'd have e to the x. Now, if I ask myself, hey, does the derivative of one part equal the other part? Now my answer is yes. Now I can let that entire denominator be equal to u. And I've got that e to the x dx that I want on top, which will change this around to be 1 over u du. And this is our special one, 1 over u du. The integral of 1 over u du, that tells me this is natural log. I'm looking at natural log of u plus a constant. And if we put that back into our original form, that would be 1 plus e to the x plus a constant. I'll pause there just for a second to say, no, we can't simplify that. Addition inside of a log, addition or subtraction, we don't have anything that we can do with that. So we would just walk away and leave that alone. But these two are like useful tricks to remember for exponentials. Oh, good question. Why did I switch from absolute value sign to parentheses? You know what? I could have left absolute values on there. I instinctively made the switch and I should have mentioned why. I know that 1 plus e to the x is always greater than 0. In fact, it's actually always greater than 1. But because I know it's always positive, I don't need the absolute value anymore. If that had said 1 minus e to the x, I could not have done that. And with that, I think it's 1 o'clock and it's a Friday. Too bad y'all have class at 5. I have office hours this afternoon from 2 to 3 on Zoom. So if anybody has questions, whether that's you're dying to know whether you got the right answer to something on the test, or you're taking a look at the homework and have questions, I've got Zoom office hours this afternoon. Otherwise, have a fun class this afternoon and a great weekend.